Hello students, happy morning. Class 12 physics. Here it is a revision video for unit 2 current electricity. Let me see the book back question from topic by topic. Okay, our first topic in current electricity, that is electric current. Let me discuss the book back question from this subtopic. Okay, first question, that is why current is a scalar. To answer this question, you have to know this equation, that is I is equal to j vector dot a vector. Okay, you know very well, dot product of two vector that will give a scalar. Okay, so current is a which quantity? Scalar quantity. Okay, it is defined as, see, the current I is defined as a scalar product of, current I is a scalar product of two vector that are current density and area vector. Okay, that is the reason why current is a which quantity? Scalar quantity. Current having the direction and magnitude, but it is a which quantity? It is a scalar quantity. Okay, then current can be positive or negative. Okay, that depends on the choice of unit vector that is normal to the surface area. Okay, it having the value of positive or negative, that depends only on the area vector. Okay, unit vector that are normal to the surface area. Okay, the next question, that is state microscopic form of Ohm's law. Okay, we know this is a microscopic form of Ohm's law, that is j vector is equal to n e square tau by m into e vector. Okay, here j is a current density and e is a charge of the electron and e tau by m, that is a drift velocity. It is mentioned as Vd. Then e vector is a applied electric field. Okay, this term, it is a constant one because having the terms n is the number of electron per unit volume, e is the charge of the electron, tau is a successive collision time, then m is a mass of the electron. These are constant. Then we can be considered as sigma. Okay, here sigma is a name called conductivity. J vector is equal to sigma e vector is known as microscopic form of Ohm's law. Okay, the next current density. Define current density. To answer this question, you have to know this expression, J is equal to I by A. Current density can be represented as J, that is equal to I by A. Here it is a ratio of current per unit area. Okay, this is defined as current per unit area of cross section of the conductor. Okay, then we know J vector is a which quantity? It is a vector quantity. Then having the unit, that is ampere meter power minus 2, because the unit of current is ampere, unit of area is meter square. Okay, then let me move for the short answer question. That is first question, that is distances between drift velocity and mobility. Okay, to answer this question, you have to know what is drift velocity and what is mobility. You have to make 3 points. Okay, drift velocity, it is an average velocity acquired by the electron inside the conductor when it is subjected to electric field. Okay, mobility is defined as a drift velocity acquired per unit electric field. Okay, it can be represented by the expression Vd is equal to E tau by m. Here it is mobility, that is mu is equal to E tau by m. Unit of velocity is meter per second, unit of mobility is m square v power minus 1 s power minus 1. Okay, see, drift velocity is the average velocity acquired by the electron inside the conductor when it is subjected to electric field. Okay, by applying the electric field in a conductor, the electron attain some average velocity. That velocity is known as drift velocity. Mobility, it is defined as a ratio of magnitude of drift velocity to the electric field. Okay, then long answer question, describe the microscopic model of current and obtain the general form of Ohm's law. This question may be asked in any other form, that is to find the relation between current and drift velocity. Okay, to answer this question, you have to draw a diagram. Okay, this is nothing but a segment of conductor. Okay, having the area of cross section A, and here we are applying the electric field from right to left. Okay, we are applying the electric field from right to left. Then here n, okay, small n is a number of electrons present in per unit volume with the same drift velocity Vd. Okay, if suppose the electron move though a distance dx in a time interval dt, then the velocity can be written as Vd is equal to dx by dt. We can write dx is equal to Vd into dt. Then electrons that are available in the given volume, that can be found by the formula volume into number of electrons per unit volume. We know the formula for volume, that is area into distance. Area A, distance is dx, into number of electrons per unit volume, that is n. Then solving this, we get the number of electrons available in that volume. Okay. Then we find the total charge. We know total charge q is equal to n into E. Okay. According to the quantization of the charge, then we can write dq is equal to charge into number of electrons in volume element. Then dq is equal to E. We know the availability of electron in that volume, that is A Vd dt into n. Okay. This is a charge dq. We need to find the current. Okay. Then I is equal to dq by dt, because current is a rate of flow of charge. Then dq is equal to NEA Vd dt by dt going to cancel. Then we get I is equal to NA Vde. Okay. Here the current that depends on drift velocity. If drift velocity of electron increases, then the current also increases, because n is a number of electron per unit volume, that is constant. A is the area of the conductor, that also constant. E is the charge of the electron, that also constant. Okay. Then this is the expression for relation between current and drift velocity. Okay. Then we need to find, what is the question? Microscopic model of current. Okay. We need to find this one. Okay. So we know current density is a ratio of current per unit area. Okay. We know current I is equal to NA Vd E, then divided by area, that is current density can be written as J is equal to NE Vd. In order to write in a vector form, we can write J vector here, Vd vector. Vd is the velocity, direction of drift velocity. Okay, that is the electron. Okay, so we can write this one as minus. Okay, we know Vd is equal to E tau by m. Okay, substituting this, here we get this expression, this minus, because of due to the direction of current density is opposite to the direction of drift velocity of the electron. Okay, so we can write J vector is equal to minus sigma E vector. Okay, but by the sign convention, okay, so sorry, but by the conventional current direction. Okay, we know the direction of current density and the direction of current is in the same direction. Okay, so we can consider J vector is equal to sigma E. Okay, then sigma, here sigma is called the term conductivity, that depends on number of electrons per unit volume, charge of the electron, then successive collision time, then mass of the electron. Okay, let me see what are the things needed to answer this question. Okay, to answer the question, we need to draw a diagram. Okay, for that we consider a line segment of wire. Okay, having the area of cross section A. Okay, then here I am applying the potential difference like this. Okay, V, after that it produces an electric field E in this direction. Okay, then the electron in the conductor attain the drift velocity Vd and moves in this direction Vd. Okay, it cross this distance dx in a time interval dt. Okay, then the number of electrons present per unit volume of the conductor. Okay, that means 1 meter length, 1 meter breadth, 1 meter height. Okay, that is 1 unit volume. Then the number of electrons present per unit volume is n. Okay, that is number of electrons present in per unit volume. Okay, here this electron moves from this point to this point, that it moves a distance dx in a time interval dt by the velocity Vd. Okay, so the drift velocity of the electron, this number of electron, that is Vd is equal to dx by dt. Okay, then we need to find the availability of electron present in that volume. Okay, so we can consider this volume into number of electrons present per unit volume, that is n. Okay, we know the formula for volume is area into distance, then into n. Okay, this is the availability of electron present in the volume. Okay, to find the okay, then we need to find dx. Okay, substitute solving this, dx is equal to vd dt. Okay, substitute in this expression, then it became a vd dt into n. Okay, this is the total availability of electron present in the volume v. Okay, then we need to find the charge of this volume, that is total charge in the volume. Total charge in the volume element. Okay, that is equal to dq, that is equal to, we know according to quantization of charge, q is equal to ne. Okay, then e is the charge of the electron, then n is the number of electron, that is a vd dt into n. Okay, this is dq. We know current I is equal to dq by dt, then dq can be written as e a vd dt n by dt. dt going to cancel, then we get I is equal to n a vd e. Okay, this is a expression that can show current that depends on drift velocity. Okay, I is proportional to vd. If drift velocity increases, current increases. How to increase the drift velocity? We know vd is equal to e tau by m, by increasing the electric field. Okay, how to increase the electric field? By increasing the potential. Okay, this is the one of the valid expression. Okay, then we know current density. Current density J is equal to I by A. Okay, then we know I is equal to NA VDE by A. A going to cancel, then we get J is equal to N VDE. Okay, here we know very well, here it is a vector quantity, so we can write J vector is equal to N VD vector into E. Okay, here we know VD vector is equal to E tau by M. Okay, it is a minus sign represent drift velocity of the electron is opposite to the direction of the electric field. Okay, so we can write J vector is equal to minus N, that is E square E vector tau by M. Okay, then we can write J vector is equal to minus sigma E vector. Okay, by the direction of conventional current, we know the direction of current density is in the direction of the current, then the electric field is also in the direction of the current. Okay, that means positive to negative. The current density is from positive to negative, and the direction of electric field also from positive to negative. By convention, we can write J vector is equal to sigma E vector. Okay, that is J is equal to sigma E. It is a microscopic form of Ohm's law. Okay, J vector is equal to sigma E vector is known as microscopic form of Ohm's law. Okay, our next topic, that is Ohm's law. Okay, first question in the Ohm's law, that is state macroscopic form of Ohm's law. We already know about microscopic form of Ohm's law, that is J vector is equal to sigma E vector. Here it is a macroscopic form of Ohm's law. You already studied in 10th standard, that is V is equal to IR. Okay, we know Ohm's law state that at a constant temperature, the steady current flowing through the conductor is directly proportional to potential difference between the ends of the conductor. Okay, that is Ohm's law. In macroscopic form, it can be written as V is equal to IR. Okay, here V is a potential difference, you know very well. I is a current in the conductor and R is a resistance of the conductor. Okay, then what are ohmic and non-ohmic devices? Okay, ohmic devices, if suppose I consider a resistor, that is a ohmic device. If suppose I apply a voltage difference, okay, in between the ends of the conductor, okay, it develop a current, okay. Then I consider a graph between that voltage and current. I get a slow line, straight line like this, okay. It is linear. For getting the slope value will be same, okay. That means the conductance value of that slope will be same. See, the device where the current against the voltage graph is straight line through the origin and that obey Ohm's law, okay. That devices are known as ohmic devices. For example, that is resistor, okay. Some devices are there. For this, the voltage against the current graph, we get a non-linear curve, okay. That devices does not obey Ohm's law, okay. That are known as non-ohmic devices. For example, semiconductors, okay. The next question, define electrical resistivity. To answer the question, you have to know rho is equal to A R by L, okay. You have to know this expression. By knowing this expression, we can easily define the electrical resistivity. Rho is equal to A R by L. Rho is a resistivity, R is a resistance, A is the area of the conductor, and L is the length of the conductor, okay. Suppose, see, question number 3, that is electrical resistivity, or it can be stated as specific resistance. Specific resistance. This is represented by symbol rho is equal to A R by L, okay. Here A is the area of the conductor, L is the length of the conductor, R is the resistance of the conductor, rho is the resistivity of the conductor, okay. If suppose I consider a conductor, okay, having area A and having the length L, okay, this is the area. If suppose the length of the conductor is equal to 1 meter and the area is equal to 1 meter square, okay, that means unit area and unit length, then the resistivity of this material is equal to resistance of the conductor, okay. This we define through this expression. See, the electrical resistivity of the material is defined as a resistance, okay, offered by the current, offered to the current flow by the conductor of unit length and unit area of cross section, okay. See, here I consider a conductor having the unit length and unit area of cross section. For that conductor, the resistance is R, so the resistivity is equal to the resistance because the area is 1 meter square and the length is 1 meter. For this case, the resistance is equal to the resistivity. That is known as specific resistance or resistivity, okay. This is the term resistivity that depends on mass of the electron, number of the electrons per unit volume, charge of the electron, and tau, successive mean collision time, okay. So the resistivity of the material will be same, okay. If suppose I consider a copper, that copper rod and copper wire, for both the devices the resistivity will be same. For that system, the resistivity value of the copper wire and the copper rod will be same, okay, because the resistivity depends on mass, number of electron per unit volume, charge of electron, and successive mean collision time, okay. It will be vary with material to material, okay, not within the material, okay. So I am saying the resistivity does not depends on dimension of the material, okay. For a particular material, it will be same. It depends only on the temperature, okay, because the temperature increases, successive mean collision time decreases, so the resistivity increases, okay. Then next question, that is define temperature coefficient of resistance, okay. For this we need to know this expression, alpha is equal to del rho by rho naught del T. To answer the question, we can construct the answer from this question, okay. Sorry, this expression, that is, it is a ratio of increase in resistivity per degree rise in temperature to the resistivity at T0 degree Celsius, okay. It is denoted by the symbol rho, alpha, and its unit is per degree Celsius, okay, per degree Celsius. Then write a short note on superconductor, okay. Superconductors, the device that allow current with zero resistance, that are known as superconductors. Okay, see, the resistance of certain material became zero below certain temperature. That temperature is known as critical temperature or transition temperature. Okay, the material that exhibit the property are known as superconductors. Okay, and that phenomenon is known as superconductivity. Phenomenon is known as superconductivity. For example, mercury. For a mercury, it behaves as a superconductor at the temperature of 4.2 Kelvin. Okay, at that point, the resistance of that mercury will be zero. Then the induced current will persist. Okay, it will continue without applying a potential difference. Okay, superconductor. First of all, to answer the question, you need to know what is transition temperature. Okay, the resistance of certain materials, okay, became zero below certain temperature, that is known as transition temperature. Okay, the material that exhibit this property, okay, resistance became zero, that materials are known as superconductors. Okay, then the phenomenon is known as superconductivity. For example, mercury exhibits the superconductivity at 4.2 Kelvin. Okay, the next question, obtain the macroscopic form of Ohm's law from its microscopic form and will discuss its limitation. We have to find the macroscopic form of Ohm's law. V is equal to IR from microscopic form, that is J is equal to sigma E. Okay, to answer the question, we need the system like this. Okay, this system consists of a wire segment having the length L and area A. This is connected with a battery of potential difference V. Then it produces electric field from positive to negative. Okay, then this, if suppose the electric field is uniform, then we can write V is equal to E into L. We know current density. We can construct the macroscopic form of Ohm's law from microscopic form. Then microscopic form is J is equal to sigma E. We can write E is equal to V by L. We know J is equal to I by A. Equating these two, we get V is equal to I L by sigma A. Here L by sigma A, length of the conductor never change, area of the conductor never change. Sigma, that is the conductivity, also never change. So this can be replaced as R, that is known as resistance. Okay, then V is equal to IR. So the resistance depends on length of the wire and the area of the wire. If length increases, resistance increases. If area increases, resistance decreases. Okay, then we can write V is equal to IR. This is a macroscopic form of Ohm's law. Okay, then let me see the limitation of this. There are certain materials and the devices where the proportionality of V and I does not hold good. Okay, we know very well that is ohmic and non-ohmic devices. That are the limitations of microscopic form of Ohm's law. Okay, let me see what are the important things needed to answer this question. Okay, that is Ohm's law. The question is macroscopic form of Ohm's law from microscopic form. Okay, to answer the question, we have the conductor like this. This conductor have the area A. Okay, area A and the length of the conductor is L. Okay, then this is connected with a source of battery providing potential difference V. Due to this, it will create an electric field from left to right. Okay, for this situation, then if suppose the electric field is uniform, we can construct V is equal to E into L. Okay, we need to find macroscopic form of Ohm's law from microscopic form. We know the microscopic form of Ohm's law, that is current density J is equal to sigma E. Okay, then we know E is equal to, we can write this expression as E is equal to V by L. Okay, substitute in this expression, then we get a J is equal to sigma V by L. Okay, hold this, then we know current density is a current per unit area. Okay, that is J is equal to I by A. Equating these two expressions, then we get I by A is equal to sigma V by L. Okay, then V is equal to I L by A sigma. Okay, this is a constant term because L is the length of the conductor, A is the area of the conductor, and sigma is the conductivity of the conductor. Okay, these are constant. We can write this one as R, that is known as the resistance. The resistance is a opposition offered by the conductor to the current flow. Okay, then R is equal to L by A sigma. Here sigma is a constant for particular material. Okay, so R is proportional to L by A. If length increases, resistance increases. If area increases, resistance decreases. Okay, this is macroscopic form of Ohm's law. Okay, one more question they will ask. R is equal to V by I. How to define resistance? Okay, resistance is the ratio of potential difference between the ends of the conductor to the current flowing through the conductor. Okay, the unit of resistance is ohm. The unit of resistance is ohm. Okay. Okay, students. Thank you. Today class is over. You have to make a key points for these questions. Okay, this is a homework for today's class. Thank you.